All right. Hello again, everyone. So we will start the second session of Monday, 9th of August. So for the second session, we will have Dr. Utane Sawangwit from National Astronomical Research Institute of Thailand. Dr. Utane obtained his Bachelor of Science and Master of Science from University of Cambridge. And then he continued to get a PhD in physics from Durham University in the UK. So for this morning, Dr. Utane will deliver a lecture on clustering. So please go ahead. Utane.
Hello, good morning, everyone. So, okay, so I will get starting. Hopefully everyone can see my screen. Let me pick the right screen. So can everybody see a slide screen?
Not yet.
Not yet.
All right, yes. No.
Okay, it's not good. Right. Let me drag a few windows into the right place. Okay, so again, good morning and hello everyone. I'm very delighted to be part of this workshop and to be able to have a chance to kind of be kind of giving part of the lectures. I will do that again tomorrow on the classification, but for today we will focus on clustering, which of course, as you might imagine, have a lot of application in astronomy. But since this will cover like hour and a half, we will have a lot of kind of ground to cover. Okay, let me try. My mouse doesn't go. Okay, it seems to be a bit of a lag there. Okay, now it's okay. Okay, now so that's working. Right. So for the outline of the talk, as you can imagine that many of these are kind of like active line of research, and so in fact what we were telling you is that in fact there's still many kind of algorithm and many kind of people are still working to improve this algorithm in terms of clustering. And so what we try to cover here, just to kind of give you a kind of a flavor to kind of what it means by clustering, right? So we'll be covering mostly three kind of topics. Okay, so that will be on the k-means, which is one of the popular one, and you will hear a lot about that. That's the hierarchical clustering. The two subjects in between that is just to tell you that k-means by itself, there's still a lot of things that you have to work toward in terms of optimization. Okay, so that will come to that in a few minutes actually. So, and then there's the hierarchical clustering. As you could imagine, once you cluster, you might care about relationship between different groups and different clusters, and if they do have or possess some kind of relationship. And then there's this expectation maximization method, or EM, not to be confused with electromagnetic wave or physics or whatever. That tend to come up a lot, and if you kind of browse the research in this field, you see the word EM. So that's kind of another way for the clustering, but rather kind of deterministic, saying that this object or this sample belong to which cluster, like a binary thing, 0 and 1. This is more probabilistic, which you will see in a bit. Okay, so to get started, we have a class on machine learning already, and you probably have heard we have at least kind of two main type of machine learning, one being the supervised machine learning and the unsupervised machine learning. So supervised machine learning, as the name suggests, you would need to, the training process, you will have a way to kind of discover a pattern, in this case, with the computer on the machine itself, as the name suggests. The pattern utilize various features, okay? Very often you heard the word feature engineering. So you have to come up with what kind of variable you want to train your data with, and try to use it for various purpose, classification, etc., etc. But the difference here is the labeling. Okay, so with the supervised machine learning, you tend to have this attribute, or sometimes called attribute, a kind of label for different class, if you like. Whereas unsupervised machine learning is more something to do with, I'm not quite sure what I'm going to discover from this data set, and you just let's just throw the data set in and see if we can uncover or discover any structure to it. So as you would imagine, the data that you would use for unsupervised learning has no target attribute, or in this case, no label. Okay, so it's more of a supervised, it's more kind of very, shall we say, very strictly kind of, you know a lot of things, what's going on, and you try to kind of get the computer to kind of come up with some sort of model. But as in unsupervised learning, things can get a bit more challenging when you try to explore data. And one of the methods that using for unsupervised machine learning is the clustering. This is a kind of a graph, a basic kind of mind map, or kind of like what if scenario, for example, what type of data you have, and what sort of scenario or algorithm you should be using. In this case, focus on scikit-learn. So as you would imagine, this is just only one kind of platform or template or kind of software package. So it's not kind of all inclusive list here. Okay, so for example, when we're starting, you know, if you have data less than 50, then you should obviously get more data. Higher than that, then you have to ask yourself what you want to get from these data or the exercise that you are doing the machine learning, right? So so I believe you recover regression last week. So for example, to predict certain quantity, you would need to go through the route of regression, right? Or if you want to do a simple kind of dimensionality reduction, that's the PCA, or the principal component analysis. And then we will have this on the left, where we want to do some kind of like classification, or basically like discover some pattern and grouping of various different objects, and whether they have any associated property to one another. Then you kind of go through the route of either classification or clustering. And then depend on whether your data has the target attribute, like we said before. So it's like a label. If they are labeled, then you go through the route of classifications. And because since those are kind of scikit-learn focused, so you can see that there are various names where basically if you try the scikit-learn, you come up with various of these different algorithms. But when you don't have this label, then you go through the route of the clustering. Okay, so again, clustering itself, you have to kind of know what you want from that. And in this case, for example, number of data that you have dictate what sort of type, what type of algorithm you probably want to use. Okay, so if something very big, there's this mini batch k-means, that's quite something specific which are optimized for you to get the answer quickly. As you will see that with the k-means, the complexity of the problem can quickly go to n to the square or into the cube. So that take quite a long time to compute, for example. Okay, so then that just to give you kind of overview pictures of what you would expect. So what is really the cluster or clustering analysis here? So basically you have a collection of group or data in this case. So you want to explore their similarity or dissimilarity, okay, depending on what you hope to get from that, or what your application is. So in certain variable space, for example, you might For example, you could plot the data, or you it could be as in terms of spatial distribution, or it could be in terms of various different scale range of parameters. Then you want to see if there's any pattern that could emerge from this data set, okay, in terms of their similarity. And then so when we talk about different clusters, mean the members in the same cluster do show more similarity, right? Whereas with the objects from different clusters, you want to kind of go toward a distinct pattern. For example, you will see in a minute what we mean by that. So really, the whole game of this clustering analysis is kind of optimized. You know, it's still a kind of like optimizing problem, as you will see. So find similarity or kind of minimize variety, if you like, in the same cluster group, which is the main thing. Okay, using some metrics to measure distance, and you will see that how do we measure distance between these data sets, for example. Clustering analysis, as I mentioned, is an unsupervised learning. So you don't need to have label, of course, but in order to assess the efficiency or the performance of your cluster, you perhaps want to have some sort of label, right? Because at the end of the day, that's what you want to make use of it. But you don't really need to have label to begin with. Okay, that's the main thing. So the kind of applications you can use as a standalone tool to get insight into, let's say you have certain set of data as a data distribution, you can do that, or you can have this as a kind of pre-processing step before you go on to do something even more complex, right? So it's a kind of, if you like, we show the kind of dimensionality reduction. This is again a kind of a similar thing, right? You have, let's say, 1,000 or 10,000 of objects. You kind of reduce or try to make sense if you kind of consider their properties. How many groups you can split them into, for example. So it's kind of a bit like that. Okay, so again, this is a summarize of what I just said. So this is what clustering. So okay, so with a pictorial kind of representation of what supervised machine learning would be. For example, you were to have a training set, okay, and could be a pair of X would be your data, right? And whereas X could have 2 dimensions. In this case, you have X1 and X2 in 2 parameter space, and then you have a number of M data point, and the label for each data point X, you have this Y, okay? So with this, and you have this kind of distribution. And so with the label, in this case, let's say if you have 2 type objects, the cross and the triangle. So when you have one point here, then you ask yourself where this object belong to, which class or which group. Okay, so how do you go about saying that where is this object belong to? In this case, you would have guessed that seeing this pattern, right, is kind of toward the lower left corner of the graph rather than upper right hand corner. So you would naturally imagine that this would belong to the group of the blue triangle, okay, which, you know, you could be right, okay, but as you can see, there's sometimes there's this outlier, or there's an object where it could scatter up into the red. So even the label itself could have uncertainties and so on. And also these are sometimes it can jump across the border around. So it could well be. So high probability being the blue triangle rather than the red cross. For unsupervised machine learning, now you can see that we switch all to, well, I mean, in this case, we don't say that red cross is kind of a type of different class, but in this case, you only have X, which now you're missing the label Y, and you see how they distribute in your 2 parameter space, 2 dimension parameters, in this case, X1 and X2. Then the question is, do you see some kind of clustering pattern? Do they reside in one corner more than the other? And whether that tell you they are kind of separate populations? So the application for this is, as you would imagine, there's various application people been using. Things like, you know, traditionally people talking about computing clusters, right? People tend to put computer that perform kind of similar functions together because they depend on similar kind of networks or similar type of disk or the similar size of RAM, for example, or social network on social platform. People or the app itself want to kind of group you into, these people sometimes they use geolocation, can group you into various group of people residing in these countries or this part of the country, or sometimes grouping you as, I don't know, scientists, students. Okay, so for the purpose of, let's say, they can have a targeted commercial advertisement to you. For example, in the same group of people, once they offer this advertisement, it's more often they will kind of click and follow and buy something, for example, or continue to see more content. So then once they kind of associate you with this group, they probably try to offer you the same kind of service, for example. And then that's kind of similar thing I put cut across into the market segmentation a bit. And then of course, the reason we're here at the astronomical data analysis, which there are plenty of example. Okay, the classic one would be just the spatial distribution. In this case, in this case here, we're looking at this Laniakea supercluster, which basically is the position of various different local galaxies in the local groups and local clusters where our Milky Way is. So you can see that once you kind of map out these 3D positions and from the light and from the position or density of these objects, you can even pick out by eyes, right? That you have various different groups of objects. And if you were to look further into their colors, for example, or morphology, then you can learn even a little bit more, okay? So this position in terms of distribution might tell you roughly where the gravity would be the strongest, right? In this case, you could talk about various clump of dark matter if you like. So in the local cluster, if you think of these as staying inside the dark matter halos, these could represent various different dark matter clump, which they kind of has merged in the past. Okay, another classic example I would say would be this kind of galaxy color by modality. When you plotting the color of galaxies versus its mass, or in this case luminosity, which is related, you do see two kind of very stark, obvious cluster of objects, one at the top there and one at the bottom. They are mostly, as you would imagine, separated by colors. So that is the plot in the middle. In this case, we use the G-R band. And the two groups, although not as strong separation in the mass, but you could see that the more radar stuff, right? So U-R or G-R in this case, the higher the number of G-R or U-R means the galaxy colors is somewhat redder, right? So the radar tend to be kind of correlated with the mass as well. And so you can see that there's very distinct two cluster of populations here. And so what else you can learn about that, of course, now, so when you start to bring in labeling and things like that, right? So the first astronomer to observe this might not kind of expect this. For example, we just throw in every data, but then he starts to realize that, hey, the thing that tend to be on the upper top there turn out to be this kind of early type galaxies, kind of elliptical galaxies, whereas the thing at the lower bottom there, the lower left, tend to be bluer kind of galaxies and have ongoing star formations, right? So this is kind of an example of what you could basically potentially discover with the data. And if you kind of examine it further, you can see in this case, in terms of morphological classifications, you could have subcluster within the cluster itself. So you can see that there are two clusters, but then you could potentially have this kind of A0 or elliptical, or you can have the spiral galaxy with bar, okay, or less bar or more bounce, for example. So you can, again, discover very different subgroup, and there's some association, like we said, hierarchical, that they could be associated with one another. Another example would be this kind of what we call the Baldwin, Phillips, and Terwich diagram, or BBT diagram, which people use to study active galaxies. As you would imagine, active galaxies, there are two main types of active galaxies, one being powered by the active galactic nuclei, or the supermassive black hole that are accreting in the nucleus of galaxies, or sometimes called AGN. In the same phenomena, you have cold gas feeding in the nucleus of the galaxies, that also kicking off a lot of star forming. So you have again, also these star-forming galaxies, and as you would imagine, when you look at the spectra of these various different galaxies and you plot them, you start to realize, without even putting the label, right, there should be something going on here, right? But once you put those label down, these are not machine learning, of course. BPD did this in 1981, so it's more of a just draw the line where you think there's a clear separation of different populations. Okay, so this is also a very good example of that. Okay, so what sort of, because we're not going to be going into all of them, so what sort of major clustering method that we could use? One very kind of simple case you would imagine, if there's a clear separation of the population, is this partitioning methodology. Okay, in this case, if you were to have a label, or even without label, right, you have two group of data cluster into different corners there, you would expect something to go in the middle. Okay, in this case, this is what you would get. So usually this kind of use a distance from, let's say, something from the middle or center value of different groups. These, of course, good examples k-means, which we will go into details later. There's of course the hierarchical methodology. One which is very popular is this agglomerative, which is the kind of bottom-up kind of grouping, if you like. So you start from something close by, like basically like we look at the galaxy clusters, right? If they are close to each other, they should be kind of somehow associated with one another, and then you start to explore further and further and further, and eventually, if you put everything all together, then you end up with just one cluster. But then you get this kind of hierarchical ladder, if you like, that you can try to associate very different groups to one another. There's also density-based methodology, which is of course also quite important in astronomy, where we the association might not just be based on distance, but rather look at the density and how that kind of falls away in the parameter where you move away from that, and that kind of gives you a better kind of connected region, if you like. As you will see later, that the k-means sometimes cannot distinguish what we call the non-convex data set, right? The regions, for example. But density-based should be able to do that. Another one is a model-based methodology. Okay, in this case, if you were to kind of have some distribution of various of your data or your populations, but then somehow you know the underlying physical model of what these populations would be. For example, this x1, x2 could be something like what we saw earlier, the color of the galaxies, or the luminous or the stellar mass, for example. Then from these, you would, you know, kind of assume certain distribution data. In this case, you could assume Gaussian. Okay, so from this in 2D, you could think that, okay, it could be some kind of combinations or superposition of three Gaussians, for example, 2D Gaussians, right? So in this case, or could be Poisson or whatever. It doesn't have to be Gaussian, but Gaussian is this, what we tend to see naturally more than any other thing. So, for example, this is Gaussian mixture model, and then you go into things like, which we will see in a bit, in terms of the expectation maximization, right, of how you would discover these various different cluster from this model. And there's other thing which unfortunately we wouldn't have time to go into this, things like spectral clustering methodology. As you can see, these two type of clusters, if you were to just naively use k-means, you wouldn't be able to get this kind of distinct, this is what we call the non-convex kind of problem. You wouldn't get this. So you have to resort to other kind of method, things like spectral clusterings and vertex and so on, things like that. Okay, so now let's look at what we mean by the k-means algorithm and why is this popular. It's kind of like a introductory thing that where it can be performed quite easily within some caveat, as you will see. So k-means, what at least, right, straight off, what is k, right? So k is the number of clusters. So right off, you have to guess in your data, you think how many number of clusters are there in your data, right? So it could be obvious if you look at the distribution of data, or sometimes it might not be. So K would be something that you kind of have to assume and put in. And of course, although some of these of your result could be deterministic, but it's also depend on K. And as you will see, complication will arise when you kind of vary number of K. So picking the sensible number of K is also very important. And as we see, we have this training set without the label. Okay, so then we can have this group of data which we can try to see or try to discover that pattern. So the process of discovering these clusters is that you start off, let's say, once you assume the number of K clusters, you start off by randomly placing or picking the data from whatever in your data set as the cluster centroid, right? So with the K cluster, you have mu1, mu2 up to mu K in this case. So you start off from those, and then you kind of taking or kind of grouping all your data, right? The data depend on how far they are. So this depend on the distance. So the data that which centroid closest to that data, then that data belong to that group. And after that, you recalculate the centroid, right? Once you get the group. So the first iteration, you have to then recalculate the centroid, and then you repeat the steps again, okay, up to, in this case, I mean, this is like a loop over the M. So first step, we call the cluster assignment step, okay, and then you kind of update the centroid, and you keep doing that until the centroid barely move, right, from the previous iteration. So then that means you converge to certain answer, right? So that sounds simple enough. Yes, it is. But okay, I said simply pass the word distance, okay? But when you come to do the clustering, what we mean by distance, okay? So if you were to use, of course, the Euclidean or the 3D space position of galaxy, that's simple, right? You use the position, let's say IA, right ascension and declination, and if you know its position, kind of a redshift or whatever distance ladder that you use, then you can use that. Okay, this term, in term distance, we generalize it as what we call Minkowski distance. Okay, just to give it more generalized definition. And so the exact definition would depend on this P value, right? As you can see here, so you can have the let's say the first object which have the coordinates, let's say data coordinate x1, x2, x unto xn. So let's say there's n-dimensional space to, let's say they have in set of parameters of the first object. Then you have this distance between the two data point, in this case x1 and y1. Sorry, between x and y. I'm sorry. Then one in the first dimension, if is p equal to 1, that's what we call the Manhattan. So basically, that's kind of city block analogy, right? For example, if you have two data points which are kind of you have to go toward the right in x 2 steps and then go up in y coordinate 2 steps, then Manhattan distance would be 4, right? Whereas in Euclidean distance, okay, you would end up with something like a square root of 4 plus 4, right? So then you got something like 2 square root 2, okay? So that's kind of different, okay? How you choose your distance, whether it's Manhattan or Euclidean, depend on your applications. Or you could go to any generic P measurement. For example, you were to kind of looking for a way to optimize or improve your efficiency or your performance, you could go all with P, for example. Okay, so this is what I mean earlier. For example, you have a data point 1, 2, 3, 4. Okay, and each of them have this 2 dimension, and you can see that with Manhattan distance, you have to go up like things like 4 steps, whereas with Euclidean, use something like 2 square root 2. The use case will dictate how you choose this distance. Okay, so that's again just so that you're aware of these. So okay, so example, a kind of a quick kind of a visualization. If you have the data set that maybe looks something like this, they're all green now because we don't have any label or we don't know what they are. It looks innocent, naively enough, like there are 2 groups here. So you might imagine you start off with k equal to 2 and see how things go, right? So you basically randomly place your centroid. Okay, it could be picking from data, it could be just randomly pick position, okay, altogether. In this case, you would imagine this is quite a good example, right? You will see the case where you can start off with something bad, and so initial starting point dictate where you would end up. Okay, in this case, if we were to follow those algorithms we say earlier, right? So the point that closest to the blue cross, okay, will be labeled in blue, right? And then the red will be, of course, in red. And then you calculate the central, as you imagine, the cross will kind of shift further in, right, where most of the data are, because that's where the weighting will happen. And you redo again, okay? In this case, now it's sort of move off into closer to the final answer, and then you keep doing it until you reach kind of converge to the final answer. Okay, so then normally once you get that, how do you represent your clusters, right? So a common way to represent cluster, of course, as you mentioned, you use centroid of each cluster. You can use radius, okay, to show the kind of the area or the coordinates, let's say, that this cluster would occupy. So as you would see that this is a bit more of a like a 1 and 0, right? You have a clear boundary. So this is sometimes we call the hard clustering or the hard boundary. You'll see the opposite end, the soft boundary in a bit. Okay, so from this, you could also, again, you can use a standard deviation of all the members within those clusters to determine how well the objects or the data spread in various dimensions. You could care about some dimension because you might want to interrogate your data further, right? If you happen to have the label of the data, you want to assess how well it does or its performance, and you might find that what you start off with in terms of number of clusters might not be optimum, and you want to kind of change those numbers and get something better, right? So then if it's in n-dimensional space, this would represent something like a hyperspherical shape. Okay, as you would imagine in n-dimensional space, okay, it could of course have elongated structures and other shape as well. It doesn't have to be just kind of like a spheroid, okay. Or sometimes people can choose to kind of represent it with this kind of classification once you have the label, right? So then you can see clearly where how that cluster come to be. But of course, this is not this example look kind of somewhat very clean in reality. Sometimes it wouldn't be so clean as we see earlier. You could have some of the 2, for example, in the 3 or in the 1 and vice versa, right? Or you could use this frequent value to represent cluster. As you saw earlier, we have this kind of histogram in bimodality, right? So you can see that there's this definitely clear distribution in the frequency of the objects in different colors bin, for example, right? So you can do that as well. What happened with cluster? So now we start to see the kind of limitation of k-means. So what happened if the kind of the morphology or the area where you expect this group to kind of connected. So if you have this kind of irregular cluster shape, things could be challenging, right? As you mentioned, the example we saw earlier. So if I were to give you the picture in the top, you might think that, okay, there's definitely some kind of connected region here, and you would go for, you would naturally expect that there's this cluster in the middle where they seem to be connected with each other. The example of this could be, morphology of galaxy. For example, you can have spiral arm, right? That could be looking something like this, but they belong to this galaxy rather than the nearby galaxy. Although let's say if you have 2 galaxies that are about to merge, for example. So this is a kind of a similar thing, right? When you kind of extract, let's say, from your image, a kind of star cluster along the spiral arm, how would you, or where would you associate them, for example? So the irregular shape would, of course, be very tough to do in this case. Like we said, using the centroid or the k-mean, this wouldn't be very suitable, as you would say. So this, what we say, this kind of region or this kind of problem is the non-convex. Okay, the being convex means that if you have the 2 members in the same group and you take the shortest distance between those two data point or the two sample, the line that connecting them, or the line that connecting the shortest distance, would be within the boundary of the sample. So in this case, the one at the bottom here giving you what we call the convex sample, okay, which of course in this case is not right. Okay, so if you would expect these to be kind of like spiral arm, the same member would cross into other region, and that would be non-convex. Okay, so what is the strength of the k-means? Okay, of course it's simple, as you would have seen already. Simple to understand and to implement. Efficiency in terms of the complexity, in terms of calculation, is quite quick, right? If you have a number of sample, you have k number of clusters, the time it takes for you to calculate is something like k times n and times t. T is being basically the number of iterations, or to calculate distance, for example. So that is quite efficient, right? As you will see later on with the hierarchical, that go up to something like n to the power 2 or n to the power 3. Okay, so that will take a whole lot longer to calculate. So naturally, you would expect k-means to be something very popular clustering algorithm. Okay, it could, terminate at the local optimum value. Okay, so this is also a caution that we need to take. Okay, the answer you reach might not be a global minimum. Okay, so now we come to this weakness of the k-means. Of course, the one of the weakness here is the way it can handle outliers. Okay, and of course, the user, you will have to start off by specifying k. Okay, so as you would imagine, would you get a different answer? You start from k, or what happens if you use a nonsensible k value, for example? Okay, in terms of outliers, as you would imagine, if you have some data like this, okay, it will try to, you said it's two clusters, so this object or this data would have to try to belong to some of the cluster, one of the cluster. In this case, it will kind of stretch out this area, okay, unrealistically, although you have only one data being outlier there, right? So you reach to the solution where it's undesirable, right? And so you could be misclassifying objects, something in between when you have something there. Okay, so one way to deal with that is basically remove the outlier right off, okay, just to be safe. The other method is to kind of do more random sampling. So basically you have to kind of do a whole lot more sampling with starting point and so on, okay? So next weakness, and also quite important, is this initial seed or initial starting point, okay, that you could basically reach what we call the local minima, and you kind of get stuck there, okay? So this is basically an example, right? You could, after iteration 1, iteration 2, and then if you pick something that is different, you could, see something else, right? So who to say this one is better than this one, although it's quite obvious, right? But, it might select into something like this, okay? If you pick the basically non kind of optimal starting point, this could happen. And again, like we said earlier, for a certain connected region, which is a non-convex region, k-mean wouldn't be ideal for that. Okay, so we will kind of, since k-mean is the algorithm that used a lot, so we'll dive into seeing a little bit of how you would optimize k-means, or kind of try to mitigate the problem that we said earlier. Okay, so one way of this k-mean optimization, by constructing this, sometimes we say a cost function, j. Okay, in this case, j could be a function of distance, a kind of almost like a variance, if you like. In this case, x data, that the distance between x and the centroid, okay, of different clusters, and then you can sum all the cluster up, or the objects up, okay, for all the clusters, and then you can have arrive at various different solutions, right, with different case and so on. And then you can imagine that with that kind of different case and different starting point, you try to optimize by looking at this j, or the cost function. Okay, so cost function would be something like just a distance square and just sum of them up. Okay, and okay, so I just keep going that. So yeah, just to minimize the cost function here. Again, this is kind of similar to what we saw earlier, right? We saw the cluster assignment, and then you have the centroid update step and so on. Okay, or you could have things like objective-based clustering. What do you mean by objective-based clustering? Sometimes when you apply the clustering analysis, you might have certain inkling or idea as to how many clusters you, or the answer of the cluster you might have, right? You might start off from certain parameters like we saw earlier. You could start off from things like you expect the elliptical or early type galaxies and the late type galaxy to do something different in terms of the colors and the stellar mass, for example. So you would naturally start off, even you don't see those, density distribution very starkly showing you, that you might start off with something like that. And then again, with the distance we talked about earlier, with objective based, you could choose to use Euclidean space. You could use Manhattan, distance, not space. And then you can use various different things. Or then you don't use k-mean. You can go to use something like k-median instead. Okay, use absolute distance between objects and the median of the group. For example, in various different dimensions, right? You can have x and y and so on. Or you can use the center. You will see a kind of similar thing here later in the hierarchical, where also you pick the distance, which is the minimum distance of the closest objects in the two clusters, or you use the maximum distance. Okay, we'll see that again. So objective-based clustering sometimes can help you to kind of start off, in the direction. So it's not all blind, right? So it's not all just do everything. So most of the time you get a much better result with this objective clustering optimization. Okay, now so let's see what you can do with the initialization. Of course, we start off with random, but random being random, right? It could randomly give you a bad point to start. In this case, if you have k point to place, right? It's the center of the clusters. You could basically, these are various different scenarios, right? You could start off with some data that looking like that, but you could end up with something that looking, in this case, if we were to assign three, this example and this example quite different. So I shouldn't refer back to that. So for example, you have these kind of like three clusters. Well, having it color label seem much better to pick out by eye, right? So naturally, you would expect something to come out, solution, something like that. But if you pick the wrong starting point, for example, with the green and the blue, closer, for example, and whatever you do, the red centroid wouldn't shift toward the upper group, for example. Then you end up with something like this one. You have the blue group here, and then the red and the green kind of split in the middle here. And of course, you can see that almost straight away that this is not, not an ideal answer, for example. And then, the example can go on and on, right? In this case. So the way to avoid this is, of course, you would imagine, then let's try with different starting point, right? Randomly. So you can do, for example, 100 iteration. And as I mentioned earlier, you then have this cost function where you can try to optimize it. Or you can take what we call the furthest point heuristic. So basically, whatever the data point that you pick, the next one that you place, try to be as far away from it as possible, right? So that's as you would imagine from our example, that would work out quite well. So make sure they are quite well separated, basically. The other example here, and also perhaps like a kind of example from scikit-learn as well. You have this what we call the k-mean plus plus. So you can kind of interpolate various different random and furthest points, or something in between those two algorithms, for example. These can be applied or can be implemented in scikit-learn, right? There's this alpha that you basically pick, right, for the distance between the point x and its nearest center. So basically, with the furthest point, you would imagine alpha approaching infinity, right? Random alpha being 0 because you don't care about the distance. So this is not depend on the d. And then with the k-mean plus plus, alpha is being 2, for example. Okay, so then once you do that, how about k, right? Once you have the cost function, you would imagine what would be your optimum answer, you go for something like what we call the elbow method here. So you vary the k number of clusters and see where how the cost function goes. And most often, once you start to arrive at the ideal solution, right, the cost function would drop down very quickly. After that, it still drop down perhaps, but it's going somewhat slower, right? So basically, this is just to try with different k and use performance measurements. Okay, performance in this case, of course, you either use what we saw earlier as the distance square from the center of the cluster, or if you have some sort of answer or label, right, could be efficiency of how it predict, right? How it predict, you have different clusters and how it give you the accuracy of the prediction, for example, right? Okay, so that's how you would kind of tackle the k-means. So now let's move on to the hierarchical clustering. Okay, so again, it's clustering, but the word hierarchical would probably tell you somewhat. So basically, you can try to, you see this all the time, right? In biology, for example, you can have the way that people groups the animal kingdom, plants, and so on together in this kind of scenario where you can have something that contain everything, and then you kind of like split into various different category. In this case, if you talk about let's say products or clothing, right? Online shopping, you could have things like, for sports and for fashions, and then you can divide that further. For sport, you have different kind of sports or fashion, and you can go into a different brand and so on, right? So a lot of time the hierarchical may be more national and could kind of give you more insight into their relationships and how they involved to one another and so on. Or you could, sometimes you can want to dive down into the little detail, into granularity, or even do some kind of pruning. Pruning, in this case, as you mentioned, if this were the tree, right, you feel that this branch is perhaps not necessary or somewhat kind of distinct. You might want to prune, as in cut it off, or have it as a separate group, for example. So most often with hierarchical, you will construct something like a tree, okay, or sometimes called a dendrogram. Okay, so basically starting off from things that are kind of closer in terms of, again, I said the word lightly distance. Okay, so the distance could be how various different features, right, could be distinguished from one another, whether they are far away from one another, and so on, right? You could have this one that close to 2, 6 would be, for example, the distance between the two objects. So naturally, you would group 1 and 2, right? And so, and then the next closest thing would be 3. So then you join 3 together with 1 and 2, and then 4 and 5, and so on. And then with these two groups could be the distance between the center of the group, that is 9, then you can join them. So that's kind of like a dendrogram. In this case, we use a kind of distance, but it could be anything, right? In terms of measuring the distance in terms of the parameters. So as you mentioned, the type of hierarchical clustering, there are 2 ways. One is like similar to what we did before. So that's the bottom up, the agglomerative. Of course, this is quite a popular one. You start off from something that looking similar to each other, and then you build it up, right? Start crossing to something, share some similarity, but somewhat further away, and so on. So you start merging something closest and then go all the way, okay? And then you trace down to root, okay? So if it's a tree, basically you start from the leaf that on the same kind of stalk or branch, for example, and you kind of come down from this big branch, and then you start to group different branches together all the way to the root, for example. The opposite end is the divisive, okay? So that's the top down. You start from something that a kind of a big group of the clustering that contain everything, and then you start to kind of look at them in details of which one doesn't share certain trait with another, okay? So then you start to break it down to children clusters. And as I said, the agglomerative, or the kind of the bottom up, is the one that is more popular in this case, okay? So each data point, then you can form into these clusters. And another kind of technical term you heard a lot is this node and so on, right? And then sometimes you can join the node together, you can merge the nodes together, right, and form things like clusters and so on, and finally everything belongs to one cluster, right? And now with the joining of the data set or your sample, there are different ways, right? So you have to figure out these links. Again, these links depend on your application that you want to use. Okay, we have something called single link, complete link, average link, and centroid link. Okay, as you will see what each of these means, and of course you could potentially arrive at a different answer or have different hierarchy or different branch based on using this kind of different definition of links. So if you were to start off with the closest data point, right, like we saw earlier, so that is the simplest case we call a single link. Okay, single link start off from basically you start building up something very close, and then you kind of like chain effect, keep going up, right? So potentially you have two clusters which have basically separated by that, and then all of them, being hierarchy, they all belong to the same class. With a complete link, you don't consider the closest one, but you rather consider the furthest point of the data that are furthest away, right? So if let's say if you were to start off from single cluster and then you kind of doing things like top down, right? So you start to kind of having this different cluster scenario, and where the members, the furthest away member, right, the distance furthest away, then you start to kind of chop up that into different clusters. And of course, these are, like we saw earlier with outliers and everything, these methods will particularly be very sensitive to outliers, because outliers by definition, they tend to be further away from the whole group, the whole sample. So these, again, very prone to outliers. And then you can go to something like average link. So you basically take a kind of centroid distance between the two groups and so on. Okay, that help you with the clustering. Okay, so this is just kind of like summing up kind of pictorial representation, if you like, of bottom up agglomerative, that you start off from something like with a single linkage we saw earlier. You have a distance between, let's say, different group A and B. You try to minimize the distance between those. Let's say you can have various different data, right? It doesn't have to be X, doesn't have to be only one dimension. So you try to minimize those distance. And again, those distance could go into Euclidean Manhattan, whatever you want to use for your applications. And you can have complete linkage. So that's the maximum. And then you have the average linkage. The other one's called Ward linkage or Ward method, that basically taking this kind of a mean of the group A and group B, and you take this kind of distance separation square, okay, and do some kind of weighting. Okay, so like I said, there are various different methods that people are kind of like area of active research to optimize this. So with a single linkage, you know that always that distance between any 2 points in a connected groups or components always some kind of less than distance r, right? Whereas with the complete linkage, you make sure that the maximum diameter is as small as possible, right, at any kind of level. The Ward method, which of course are more kind of optimized, a more kind of add-on, is to kind of working quite well in any circumstances, which basically that would kind of merge two clusters that would increase the k-mean cost, for example, right? So that it means that with the so when you're dividing the group, right, to optimize this cost function, if you merge the two groups and then you kind of get the cost function to be lower, this would happen, right? So this is what the Ward method is trying to do, to basically minimize the cost function if you can merge the two clusters into the same group. So now come back to the complexity of the problem, like the calculation time and so on. All the clustering, like we saw earlier with the k-means, and also hierarchical. Hierarchical is even worse, right? Hierarchical could be even n to the power of 3, but of course you could come up with some kind of optimized implementation in the coding that you can reduce it to n to the power of 2. So the worst case scenario tend to be the order of n to the power of 2 for your data point. So you as you can imagine, if you want to iterate with different k cluster, number of k clusters, or you want to iterate with different starting point, these would start to kind of it could become a forbidding factor for you, computationally, in order to kind of get the optimal answer because of the complexity or the calculation time here of n to the power of 2. So you would imagine things like k-means then become quite popular or quite attractive in this sense, because you only have something like k time n and time whatever number of iteration or the distance that you have to calculate between different objects, although the distance between objects you only calculate once. And then things like complete and average link, can be n to the power 2 log n, for example. Okay, so for these complexity, as you would imagine, it's quite hard to use with the large data set. Okay. Okay, now we have the kind of final half an hour. Let's move on to the expectation maximization method. Okay, which is somewhat kind of more probabilistic. What we saw earlier, you can have a clear boundary of different clusters. Either it's in a line if you have two-dimensional data, or is this a kind of surface if you have three-dimensional data, or hyper surface if you like, in whereas n-dimensional surface. So it's more of a 1 and 0. So once you have your machine learning done, you put your objects in and you ask what this object, which cluster it belongs to. It just only give you single number, right? It belongs to cluster 1, 2, 3 or ABC, whatever, depending on how you call it. With the expectation maximization method, you want to do something that we say is not a hard assignment. Okay, so with the limitation of k-means is to address this hard assignment of the data point to the cluster. As more often than not, is that you tend to want to know, sometimes you just that this classification, you want to know how confident you are, right? That this object associated with this cluster, and perhaps there could be some association of this object to the other cluster. You don't want to just basically know that it's just belong to this cluster, but it's not with the other cluster, because sometimes that is not very helpful, because it could be wrong, but you just want to know how most likely it could be right or could be wrong, or whether the association with the other group is stronger, or are they kind of like similar, something in the middle. So you cannot say for sure that this is this group for sure. So this kind of expectation maximization is kind of something to address this point. Sometimes it's called a soft kind of soft limit or soft boundary, if you like. Okay, so basically once you have placed an object, instead of you get the machine tell you this object belongs to which cluster, you get instead the probability that you expect this object to associate or be in these clusters and in the other cluster and whatever other cluster that you have, right? So that can be quite useful. Okay, so this is what I said, the soft probabilistic assignment. Okay, which could be interesting, right? As you saw earlier with the k-means, if you start off from the wrong or nonsensical value of k clusters, or with the different starting point, you could basically arrive at something that doesn't make sense. So probability could potentially help you with that. So okay, so sometimes you heard things like Gaussian mixture model. Okay, so what the expectation maximization does is then basically it's a kind of like algorithm, okay, to find if you were to start off, let's say k is 3, right? Let's we'll see in a bit in terms of example. Then how would you construct those 3 different Gaussians, right? Where to put them, and what's the centroid, or in this case mean value, or the variance, for example, would represent how narrow or how wide the Gaussian distribution is, right? And how they all add up together. So we will take a kind of look at this, what we call the mixture of Gaussians, right? Kind of this Gaussian mixture. Sometimes you heard it as a GMM, the Gaussian mixture model, right? So, for example, you start off on some kind of distribution. You might imagine as you would think, right? When you see things like in astronomy, you might look at spectra of an object, the light that come from the object. You can see various different lines that could be broadened, and sometimes it's not just one peak. And so sometimes you see that if there are distinct peaks, you throw in, so let's say 2 components Gaussian, right? Double Gaussian, for example. If we talk about bimodality earlier, then you probably want to try with the 2 Gaussians, right? So that's basically, what you think you can try to fit the data, right? With put in enough Gaussian. Of course, with more Gaussian or more cluster, you end up with a higher number of degree of freedoms or parameters that you can tune. So you go into the territory where we call the overfitting. So it's quite important not to overfit the data, right? Because if you overfit the data with your training set, you might get something very good result. But when you actually use it in the real data, because of your overfitting with different Gaussian, right? You can have various different small Gaussian, adding like 10 Gaussians within the data. It could fit your test or your training data set very well. But then when you put the data in, all hell can break loose, for example. So this is quite important as well. Although, you think, yeah, with enough components, you can fit anything, but then you wouldn't go all out of putting a lot of things, right? So basically with this Gaussian, you can use the probability distribution function, right, to help you with that. So when I say Gaussian, it could be variable, multivariate, right? So it doesn't have to be just one dimension. In this case, X could be a vector of n dimension, right? X could be, in this case, X, Y, Z, or whatever. It doesn't have to be position. It could be various different parameters, like we saw earlier. It could be colors, G minus R, could be the magnitude of the galaxy, it could be the stellar mass, and so on, right? Or the size, or if you were to measure the morphology, you could measure things like ellipticity and so on, right? So that, what we mean by multivariate Gaussians. So basically, you try to construct this kind of multi or higher dimension Gaussians, and this, as you would expect, right? So this is basically the what you get, a kind of a likelihood, or the kind of the Gaussian likelihood. Normally we take log of this. So this is kind of like describing the Gaussian function, right? So you have X minus whatever here, the mean value, and then you can normally you would have this X minus mean and then square, right? In this case, we, instead of using below, you usually have to sigma square. So sigma square is a variance. So what this sigma, this big sigma with -1 is what we call the covariance matrix, okay, which is quite important, right? Most often, different parameters or different, what we talk about, different parameters in different, dimension we talk about, most of the time they are not independent, okay? Because if they were independent, the covariant matrix will reduce to diagonal matrix, which means then you can reduce the form down to what you would normally quite familiar with, right? Is X minus X bar to power of 2, and then divided by 2 sigma square, which is the variance, basically. In this case, this is a more generic term and more generic form you like, okay? So you have this covariant matrix, and this is basically an inverse of the covariant matrix, okay? So if you were to have diagonal matrix here, then you would reduce this down to just 1 over sigma square, okay? So this is what it is, okay? In case of inverse covariance, which is this lambda thing in 1 dimension, you would reduce this down to sigma square. Or if you were to have a diagonal matrix, which means the other, there's no cross correlation between different terms, then you end up with variance, okay? So this is a more kind of generic representation, if you like. Yeah. Okay, so if you have a data set D, n data point, okay, and X, of course, capture, like we said earlier, could be in this case we use n, right? M dimensional, right? And so with this probability, right, or sometimes we call likelihood function of these function, of how likely it is, for example, given if you know, for example, if you know the center of the clusters or center of the Gaussian, in this case mu, and if you know, so we start off from, let's assume we know, right, there are let's say 3 Gaussians and where they are centered at and their distribution in terms of their variance. Okay, then this likelihood or the probability would be just the multiplication of all those terms add up together, right? So from n equal 1 to n. So this is basically different Gaussians, right? You have various different, let's say you have n cluster in this case, right? N Gaussian components in capital M. Sorry, I have to make that explicit. So then basically you would multiply all those together, right? And most often to represent likelihood function, we take log of that. So basically log of something, you know, multiply and you end up with something as an addition, right? So with the likelihood, okay, take log of that, then you end up with something like this. Okay, you have the term where you've got a covariance, you've got these terms here where basically how far away from it, from how far away each data from the respective center. Then you kind of, then what you try to do, then you kind of maximize this likelihood, right? So now you have this kind of so this is a bit like a cost function earlier, right? You saw this cost function earlier. So now what you want to do here to basically figure out mu. Okay, if you have if you vary n as well, number of Gaussian component, you vary n, you vary mu, you vary if you don't have assumed covariance already, then you do that as well to the point that you end up with likelihood. This is the minimum. Okay, so that's what the solution we're trying to achieve. Okay, so with the maximum likelihood, mu could be written in something like that. So for example, the mean, this is of course this is example mean, right, of all the n sample would be just a simple divided by n. And whereas if you are to maximize respect to the covariance, so basically what this is so really you kind of differentiate this function, right, with respect to either mu or either to this sigma, this capital sigma, which is the covariance. Okay, so then you end up with something. This would be the solution to the differential equation of those, and then set it to 0. And then for the covariance, you end up with something that look like this. Okay, so which basically you need this kind of information from the mu ml, right? And then you have this to get the covariance of the that have at the maximum likelihood. So again, so what we say, this is as a Gaussian mixture. Hang on a minute. Let me just, okay. I was going to say earlier we didn't assume Gaussian, but actually we did that assumption of the Gaussian. So anyhow, so let's say if we were to have this Gaussian superposition, right, of these different k. So now let's say we have a k cluster or k number of distribution. Then you have this kind of a function. Let's say if you talk about like landscape of how likely where you expect to find your data. So it would be represented by this. Okay, so each cluster would then kind of described by their centroid. Okay, so mu k and the covariance matrix. Okay, or variance basically, right? So but just to allow things to kind of correlate, then you have a covariance here matrix. So this pi k is there just for normalization purpose. Okay, so oops, sorry. Okay, so you would imagine that basically this would be kind of like we try to there's some kind of like coefficients, right, as a it has a prior, so we could have some kind of prior in as well. Okay, so this is kind of related to what I think you covered in last week on the Bayesian statistics, right? So you don't have to start off from something kind of without any prior knowledge, right? So like a frequencies approach, you could basically, if you think the possibility, for example, here p given cluster K, right? What the probability that you have this X data point given the cluster K, then you can have this sort of prior kind of throw in, right? So in this case, if you were to kind of start off from mixture of three Gaussian distribution, as you can see here, it doesn't have to be perfectly like I mean because of the because we have the covariance matrix, so it means that in this case you can have the variance, right, in the X, let's say the horizontal direction is X and vertical direction is Y. So then you can have this, it doesn't have to be symmetric, okay? So it can be elongated in this sense, right? So then you have can have different orientation from different distribution, Gaussian distribution. They can have different peaks or cost amplitude, okay? So this pi k here take care of that. So once you add them together, so this is originally you have these three Gaussians. Once you add them together, you would imagine start to kind of like represent them by contours, like we saw earlier with the bimodality. So it starts to get a bit complicated, right? It doesn't have a clear kind of Gaussians that you would imagine, but you can see, you can kind of like pick out perhaps there's this three distinct region, or someone might go for four, right? Once you add this, if this is the let's say you plot your data in 2D histogram, you see this, you might think, oh, okay, this looks like there's 1, 2, 3, 4. In fact, you might start off from actually 3 components, right? So this is the area where, like I said earlier, the K number of cluster could be something that you have to optimize towards. So if you look in 3D, it could be looking something like this, right? So each peak doesn't have to be all the same. And the center, when you add up, is kind of like adding the amplitude all together and the likelihood and so on from that. So now let's say if you were to try with that, okay, if you were to run some kind of simulations, start off from those Gaussians, you can try to generate data point, right, based on those probability. Then you can pick some components with probability, in this case, pi of k, which is basically what you get from the exponential over there, and draw sample in sample from each sorry, it's the total from all the Gaussian, not just from each Gaussian. And X, then like we said earlier, it doesn't have to be one dimension. So repeat these steps to get, you know, basically more and more data point. So once you simulate those, right, because it's Gaussian, then it could be kind of like everywhere. So in this case, we have a clearly labeled colors, right? Because it's this is a kind of going, you know, backward a little bit from theory and see what we can do with that. So you start off from this. You have these three distinct sample from the three Gaussians that we saw earlier. So now let's say if we want to kind of, let's say if we try to forget that these are different colors and to have this kind of the whole sample that are just distributed in your two parameter space like this, and try to uncover their distribution. So you start off with looking at this fitting of the Gaussian mixture. So again, let's say if we start off with the three components or whatever, okay, so this whole thing is just invert the process, right? So what you need with those is these mixing coefficients, right? So mixing coefficients we saw earlier is basically the relative amplitude, because the three Gaussians need not have all the same amplitude, right? So you can have different kind of significant contribution from various different populations, basically. And then, of course, you have the means from different Gaussian to locate where they are in the parameter space, and then you have the covariance. Okay, so of course, with the problem, the data set, we assume that it's unlabeled as we show here, and then try to reach that final answer, or rather recover the Gaussian distribution. We go through the route of maximum likelihood, like we saw earlier, but we'll see how this will be implemented with the data, right? Although with the label, we can, you know, say this is actually latent, so kind of hidden variable, right? So we don't use it, although we, you know, here we know is generated from that. In the case of bimodality, we know that the galaxy type, whether they're early or late type, and morphology, but you know, it could be some kind of extra information. We might not use it here. Right?
Utane, it's 15 minutes.
Yes. Okay. I think we should getting there. Should be getting there. So with what we saw earlier, right? So what we try to cover with the data, we try to construct this, basically trace out this posterior probability. So again, we saw from the Bayes theorem, right? With the probability. So with this set of data, you try to kind of guess, or with the data that you have, try to kind of invert the process and say, let's say if you try to construct this, like a likelihood or probability map, okay, how it would look like, right? Here, what this is here with the gamma k. So if you have this k clusters, a probability that if you have a data x, right, it would associate with the cluster k. Okay, so what we're trying to recover here is this kind of Bayes theorem kind of probability posterior p, where we have position x of the data and how likely it is to be in cluster k, right? So if you follow this kind of Bayes formalism, right, then you come to something like this. Okay, so you have to kind of basically calculate or implement the numerical to recover this. Okay, so of course this n, as you saw earlier, then you have to kind of like go through various different iterative process to discover mu k and sigma k and so on, right? And then so let's say once you do that and you maximize the likelihood, in this case the likelihood would be the cost function similar to what we saw earlier. You end up with something that kind of like this. So as you can see, it's not all blue, it's not all green and red. You can see there's a different shade to the blue and to the green, right? So the more light blue, let's say, so the more likely it is to associate with that cluster. And you can say that something like this almost look like a mixed color of the green and the red. Is kind of represent the area where it's possible that there's a high chance it can be green and also red. Okay, so now you start to see something like what we call the soft boundary, and also this area as well, the blue and the green. And as you would imagine, right, the stuff that are up here or down, sorry, the mouse is wrong place. So either up here or down here, right, it would be a safe blue or safe red, right, because they are very far away from those areas where things get a bit messy, right? So these are data points that you throw in and ask what the probability, but in fact it is actually map out this kind of the whole space, right? So you can map out the two space and say that, okay, so it doesn't just limit it to your data point. So basically if you were to put your finger on to some area, right, you would kind of get that. So this basically is a posterior probability map. So if you were to put your finger here, then you would think that these would more likely to belong to this green region. But if we go back a little bit, you can see here that there's no data point here at all, right? So even that, we have to be very careful, right? So there's all missing data or whole the data here, but we kind of extrapolate a little bit here that the Gaussian could be continuing all the way here, although it's very unlikely to be here, because if the Gaussian were to peak here, out here would be something, like 2-3 sigma away, for example. So it's quite unlikely to be 1. Okay, so you have to be also careful. So what end up here in this case is this kind of posterior map rather than a hard boundary. Okay, so talking in terms of the math, of course, with the likelihood we saw earlier, right? We take a natural logarithm of these, then you have a sum of these, depend on how many clusters you have, right? K clusters, here you have the n number of assumed value of these different Gaussian components, right? So this sum over the components here, and what you do is then you look for the answer, in this case mu k, phi k, and even the number of clusters itself, right? To look for the answer where it gives you the maximum likelihood. Again, there's this caveat here. There's no closed form solution. Okay, so it's mostly kind of numerical that you normally trace out this posterior. Okay, so in this case, that is the problem, right? And what you trying to do is to maximize the log likelihood. Again, you solve for that by what we say the expectation maximization or EM algorithm. Okay, and again, avoiding various pitfall things like singularity and so on. And you can apply things like a Bayesian treatment, like we said earlier. Okay, so again, things like K, the number of cluster, number of Gaussian component here. How do you get it? Again, you get that from try to minimize, cost function in this case, maximize the likelihood. Okay, so the algorithm could, could be looking something kind of like this. Okay, mathematically, you kind of differentiate those likelihood we saw earlier, set it to 0, right? And then you have this relationship, or rather for various different parameters here, mu. Okay, then you end up with something like this, which is actually just the weighted mean of all the data, right? And again, for the covariance, right? We saw earlier we can have, because it's depend on mu j and covariance, you can then differentiate with respect to mu j, and then or with respect to sigma in this case to get the covariance, to discover this correlation of your parameters. Also quite important. So then with that you get to something like this. Okay, and also there's this pi k or pi j that in front, which basically tell you the relative importance of different distribution or relative height, if you like, of or normalization of different one. Okay, so it will give you this term here. So that is all kind of like mathematically solving. So with this, then again, just to reiterate that the solutions here is not closed form. Okay, so they are kind of coupled to one another of how you reach to the final solution. So usually how you solve this is through something kind of a iterative process. Okay, you make something like initial guess, again very similar to almost like a k-means, but here it's more probabilistic. Okay, then you alternate the two states we call the E step, which is the evaluate the responsibility, okay, function, and what we call another one is M step. You update the parameters. So once you kind of calculate the centroid, a bit like k-means actually. So with that you recalculate the likelihood. Okay, so that's called what we call the M step. And again, you kind of go on and iterate the process. Okay, the pictorial representation would be something almost similar to what we saw earlier, right? This example where we start off from the 2 point in the k-means, one in the corner here and one in the corner here. So let's say you start off from something like a Gaussian to component Gaussian here, with of course with the sigma x sigma y, a kind of like a similar size and so on. So that's kind of like tell you what covariance would look like. Okay, and you start off with that and you see how these points are associated. Okay, so these would represent the probability that is associated with this group, and this is associated with this group. Okay, and with that, akin to kind of like you calculate the centroid, but here instead you kind of evaluate or maximize the likelihood, okay, function as we saw earlier. Then you end up with something more like that. Okay, so you end up with a centroid shifting to new positions, and of course you end up with the new covariance. Okay, that looking something like that after the one iteration. And the colors, the shade of the colors, again associated with how likely you think it's going to be with different groups. And you can keep going. Okay, so after like 5 iterations, okay, so now I'm mute. Okay, so let's continue. So again, so after like 5 iterations, you start to see things start to converge. But again, the point around here, you start to see still have much of the blue, because the blue appear to be somewhat wider than you would hope, right? Because it's quite clear there's this good cluster here, and then you keep doing. Let's say after 20, why my slide's not going? Okay, so after like 20 iterations, you start to kind of like get things answer which is pretty good. But again, these are probabilistic, right? So it's not a sharp line that draw through here. Okay, so you would have even the point here, you would have associated probability that this point could be associated to this group as low as maybe, right? But then again, it will be up to whoever that use the data to make the decision which cluster you think you believe. For something in the middle, you could have, you know, two peaks that probability that looking kind of similar, and then you can judge whether or pick which one you would like to use, or you think you believe in what cluster it belongs to. Okay, so to give a quick summary as the last slide here for the clustering. Okay, so clustering analysis we saw is quite a versatile tool. Okay, to pick out the pattern. Okay, so for the machines to learn to pick out this similarity or dissimilarity pattern that has a broad range of applications depending on what you're trying to use it for, and even those distance definitions and linkage is also can be tuned to answer to your different applications. Okay, so is very important, and we'll have also very important final outcome to the final outcome of what you hope to use those for. And the clustering algorithm can be categorized into different way, right? We see this partitioning, which what the k-means belong to. Okay, and then there's a hierarchical, which you know, focusing on who belong to who, or if you go down from the root, whether these two objects are closer or similar than the other, right? And so on and so forth, for whatever various reason. And that's just basically highlighting different applications we saw earlier. We didn't quite cover the density base, but it's also quite important when you need to kind of address things like non-convex area and various other things that is not just based on the distance alone, right? So it's sometimes you have this density base that help out. We look at this model base a little bit in terms of the kind of like Gaussian Gaussian mixture model, and using things like expectation maximization or EM to kind of arrive at the optimal answers. And then there's something called spectral clustering, and also ensemble methodology, which are a whole lot more complicated and also very important in various areas where you start to kind of exhaust the ability of things, you know, simple case like k-means to do to help you out with the machine learning. And again, like I mentioned in the beginning, there's still a lot of research, right, that people are still carrying on with the cluster analysis, things that because these are unsupervised machine learning, so you can imagine the power, how powerful this method could be without having to label them, right? Usually with the data, you have to label what class they are and things like that. You need certain kind of label force, and again, even label, there's also label uncertainty that you can get trapped with. So okay, so it has the potential to also handling a massive amount of data, the big data, of course, high dimensionality, right? So it's a bit like a dimensional reduction that help you with that. And one thing we haven't quite talked a little bit here in terms of the performance evolution, right? Things like when you need to have a label, or at least you know the answer to evaluate the performance, and then instead of minimizing the cost function based on distance, you could be minimizing the cost function based on this performance evaluation. Let's say if you have a label, right? Whether you can classify it correctly or not. Okay, but that is another kind of topic related to what we will cover tomorrow with the classification. Okay, so that's all for me. Thank you.
Thank you very much, Dr. Utane. So maybe I would like to invite quick questions from the participants. All right, so Isan is asking a question. So please switch on your video and unmute your microphone, and you can ask directly.
Hello, am I audible?
Yes.
Okay. Thank you for the lecture. I had a question that you said that to find the best value of k, we basically use the elbow method and plot the cost function versus k, that is the number of clusters. Do we do something similar for the Gaussian mix model? And are there ways to do it in machine learning packages like scikit, or is this something we have to do manually?
Sorry, let me try to repeat to see if I get all the questions. You asked if this is something you do manually or?
Right, like do we have to evaluate the cost function on our own, or is there like already pre-built functions in machine learning algorithms to do it?
Okay, so that's depend on your applications, right? When you do the k-means clustering and various other things that have these kind of free parameters, you should always aware that final answer may be depending on these parameters that you first assume. So it's always very important to, once you realize that, of course, then the questions of whether you do it manually or there's some algorithm that can do this for you, it's depend on how you implement it, right? So you use things like scikit-learn. You could use certain functionality if you like to do that, but if you kind of write your own code, you could basically fold in another, I don't know, loops to kind of explore the k, and also depend on how fast you can arrive at the answer. If your sample is quite big, that will take quite a lot, quite a long time, and then and it's probably an ideal case to have it kind of run in your pipeline rather than you having to wait for one to finish and then try a different case and so on. So yeah, so that's quite important. A similar thing, this is the same problem with optimizations with the starting point and things like that. So usually people use sometimes this kind of Monte Carlo process, right, to kind of, instead of starting at some point, you kind of do iteration like randomize how you start and things like that. And so that's kind of a similar thing to things like when you do like Monte Carlo Markov chains, things like when you do a parameter fitting. So that's that as well. So you can wrap up things like Monte Carlo process to help you out with that.
Okay, thank you.
Thank you.
Thank you very much, Isan, for the question. So I think we are already over the time. So for anybody else who have a question, please hold on. You can still ask Dr. Utane tomorrow.